So hello friends, welcome to my channel MN Coaching Center. So today I'm going to explain your 12th standard physics second chapter, that is electrostatic potential and capacitance, part 2 video. So last video I explained about relationship between field and potential. So let's continue from potential energy of a system of charges. From here let's continue. So let us so in last video we get the formula. In last video we get this formula in the potential energy of charges. There we got the formula and potential charges in dipole. There we got this formula, that is 1 4 pi E0 into 91 by RLP. This formula we got. So let's continue that formula. Work done is equal to 1 4 pi E0 into 91 Q1, that is electric charge, in 1 into electric charge 1 by radius 1. This formula we got, and that formula we are using since the electrostatic force is conservative. This formula we are using for electrostatic force. U is equal to this for, since the electrostatic force is consecutive, this work gets stored in the form of potential energy, and that potential energy of two charges are called as Q1 and Q2. As I said, potential energy, it is potential energy. So obviously if Q2 was brought first in the presence of location of Q1 brought later, then the potential energy U would be the same, then the potential energy U would be the same. It will be the U potential energy will be the same if first Q2 is brought first, then before Q1, then the potential energy, that is we also say it as U, here U would be the same, they are saying. So this is the equation. So equation is easily generalized for system of any number of point charges. Let us calculate the potential energy of a system of three charges, Q1, Q2, Q3. Let's see three charges potential energy, how it will be. So let's take Q2 charges potential energy into V1 is equal to 1 by 4 pi V0 into Q1 Q2 by 12. So now what we will do means that Q1 by R1P plus Q2 by R2P, what will do means that we will do whole square. What will do means Q3 V112 is equal to 1 by 4 pi E by 0. So Q1 by Q3 into R13, Q2 by Q3 is equal to R23, like this we will write. And next what we will do means Q1 by Q2 plus by R1 by 2, Q1 by Q3 is equal to R1 by 3, Q2 by Q3 we will do it as R2 and 3, like this we will write this formula. Again, because of conservation nature of electrostatic force, because of that static force, the final expression for U is independent of the manner in which the configuration is assembled, and the potential energy is characterized in the present of configuration and not the way the state is achieved. It is not written in the way that state is achieved. It is the potential energy is written in the way of electric configuration. So these are the some sums on that, so you have to calculate. Next is potential energy in an external field. In a single charge, how will be the potential energy if there is a single charge? So they are saying, so the charges or their locations and the potential energy of the system of those charges was determined. So in this section we ask a related but a distinct question we may ask. So what is potential energy of a Q in the given field? We may if they what is potential energy if they ask means the starting point that leads us to the notation of electrostatic potential. But here we address the question again and clarify. Let us clarify it by doing discussion on it in section 2.7. Here 2.27 we will discuss it, and we will clarified it in 2.7. We clarified it just now. Last I explained 2.7. There I clarified what is that what we get in electrostatic force. There the formula that we get, this is only the potential energy I clarified. Therefore that is potential energy. So this is the potential energy formula I clarified in the last video. So the main difference is that the now concerned with the potential energy of charges is an external field, and this external field we call it as E, and not produced by the charges. That external field is call it as E, and even if Q is finite, it's Q that charges if it is finite, its influence on the external force may still be ignored, and in this situation when a very strong source far away of an infinity produce infinite field E, if it is finite, the external it is in E region of interest. So we have to note again that we are interested in determining the potential energy of the given charges in the external field, not interested in potential energy, that formula we got in producing the potential energy. Not we are interested in of finding the potential energy, not producing. Okay, so now thus the work done in the bringing charges of Q from infinity to the point P in the external field is Q. Let's take as QV, and therefore potential, and also we can take it as R, the external field, or R. And let's take the, if the point P has position of vector, let's take vector R, vector as R. So q and small q and capital V into R, let's take like that. So thus if an electron with charges Q is equal to E is equal to 1.6 into 10 to the power of 19 C is accelerated by the potential difference of 1 volt. If delta V is equal to 1 volt, if it is, then 1.6 into 10 to the power of 19 C is the electronic charges it has. We have to understand. So potential energy of a system of two charges. What if it has two charges? So Q2, let's take R1 and R2, that is vector 1 and vector 2, let's take two vectors. So Q2V R2, let's take like that, Q1 Q2, and let's take 4 pi electric field R12 R1 and 2, let's take 12, not it is 1 and 2, and just the potential energy, let's determine it as Q1V R1 plus Q2V R2 plus Q1 Q2 4 pi electric force and R1 and R2. Let's take, this is the formula we get when the two charges are there. So if single charges are there means QVR we will get. If two charges are there means we will take Q1V R1 plus Q2V R2 plus Q1 Q2 plus 4 pi E0 R1 2, like that we will take, because there are two charges. In first if potential energy has one charges, we will take like that. So there here it has some questions based on this topic, so you have to solve these questions. So potential charges of a dipole in an external force. So dipole, that formula we got. No, this is the dipole formula. Work done is equal to theta by do is equal to theta by sin theta by dipole theta. So this is the formula we got there. Angular acceleration. So power into electric field, and the T is equal to, we are taking. So this is the dipole formula we got here in last video when I was explaining. This is the dipole formula we got. So here in dipole, as I was explaining, see here dipole I was explaining, and here we got the formula of the dipole here, cos theta we got like that only. Here also we are getting the formula of the dipole. We are putting that formula of the dipole to external force or electric field, or electric field also we can say, external field or electric field here we can say. So we will take, what we will take means potential energy U is equal to PE, PE or the potential energy or power into electric field or electric field E by cos pi by 2 minus cos theta is equal to minus PE cos theta is equal to minus P into E, like that we will take. And what we will do means that formula we got now in potential energy of a two external fields, that formula we will put here, and here we will not take it as R2 R1 R2 like that, not 2A we will put. And now what we will do means we will put both we will join both of these, and we will write the answer that we got is potential energy is equal to Pe, that is the potential or power into electric field cos theta minus Q, that is charges 4 pi V0 into 2A is equal to P into E minus Q square 4 pi E theta E0 into 2A. The formula we got we will put here, and that by using that we will solve, and that plus or minus, if it is, we will get is the opposite or cancel out. If we do, then we will get is here PE or there, here also PE or there, cancel. If we do, we get Q VR1 minus VR2 is equal to 0. This we will get like this configuration we will get. So next is, the next thing we are going to do is the some we have to solve. Next is electrostatic of conductor. So how will be electrostatic in a conductor? So conductor contains mobile charges, carriers in the metal conductor. These charges carries or electrons. As you know, in a conductor, in a wire, they carries electrons to electrons, and in the metal, the outer electrons part from their atom and are free to move. They are very much free to move. As you know, they are very free to move inside the inside the wires. And there are positive ions are made up of nuclei and bounded with an electron, and these electrostatic conductor, they have positive and negative ions, both they have, as you all know. So if this movement of charges carries is affected to both external electric field and as also by the so-called chemical force, it is also called as so-called chemical force. If it affects to the external electric field, here we got no, if it affect to that. So inside a conductor, electrostatic field is 0. How it is 0? So let's consider a conductor that has a neutral, or it has charged, positive or negative charge, anything you can take. So there may also be an external electrostatic field it has. In that static situation where there is no current inside or surface of a conductor, there we can say the electric field is 0 everywhere inside the conductor. We learnt in the first video as I was explaining electrostatic. There I said every conductor, if every conductor electrostatic is 0. So this fact can be defined properly in the conductor. A conductor has free electrons as long as a field as long as field is not 0. The free charges carries would experience force and drift. They may experience force and drift. In the static situation, the free charges have so disturbed themselves that the electric field is 0 everywhere inside. So they both have disturbed themselves. The electrostatics have disturbed themselves. So by that they both are 0, we can say. So at the surface of charged conductor, electrostatic field must be normal to the surface of every point. The electrostatic or electric fields, since E means in, sometimes as I last year I was explaining that formula, the electric field, that is E also, capital E also they give. So normal. So if E were not normal to the surface, it will have non-zero components. It will be electrostatic will having non-zero components, and also E should have no tangential components. So thus electrostatic field at the surface of charged conductor, that must be have normal to the surface at every point to the surface. The electrostatic field should be normal then. So next we are going is the interior of a conductor can have no excess charge in the static situation. So remember this all. In this they may ask anyone for in your final exam. If asked means you have to write. So a neutral conductor has equal amount of positive and negative charge in every small volume of surfaces. When the conductor is charged, the excess charge can reside only on the surface in the static situation. Thus follows from the Gauss laws the learnt. Consider any volume element we can consider and closed surface bounding the volume. Let's consider like that. So we can say that the field is 0, as you know, electric field or electrostatic field is 0, we can say. So then the volume V can be made versatile small. This means that there is no net charge at any point inside the conductor, and any excess charge must reside at the surface, we can say they are saying in this thing. So electrostatic is constant through the volume of the conductor has the small value on its surface. So in a system of conductor is orbitally size, shape, charge, configuration, anything characteristics consist of the potential, but this constant may differ from one conductor to another. It may differ, as you know, the according to its conductor size it may be, the electrostatic force may be differed, we can say. So next let's come to electric field at the surface of the charged conductor. So this electric field formula you have learnt in last video. I have showed you that I have showed you. So by using this formula only, by using this is the Gauss law, by using this Gauss law or this formula, Gauss law or Gauss formula, E theta S by that we will do E is equal to theta E by 0 we will get. This is the formula of Gauss law. So electrostatic shielding. So here the electric field inside a cavity of any conductor is 0. All charges reside only one on the other surface of the conductor of the cavity. Their cavity and reside only outer surface of the conductor. With cavity there will be outer surface. So here see conducting body, and here is electrostatic field, the outside positive, negative, they are electrostatic conductor, and here the theta or the sigma is equal to 0. They are saying here the sigma is equal to 0, sigma is greater than 0. So they are saying in this electrostatic the sigma is greater than 0. It will be the field inside the cavity is always 0, or it may be the if it is always 0, then we can say it as electrostatic shield. That is electrostatic shield, we can say. So next let's learn about the next topic, that is the dielectrics and polaristic. So in this conductor, the difference behavior of a conductor and dielectric is an external electric field. It has external electric fields. Here you can see, here this is conductor. So conductor is having the sigma, and it is free. One side it is free, one side not, both the side the sigma, positive and negative, both the side the sigma electrons are free. And here electrostatic force electrons are they also same, but here what happens means the electrostatic force and electrostatic in is not equal to 0 in the dielectric, but here in the conductor they both are equal to 0, they are saying. So if they both are not equal to 0, then we can say that is dielectric. If the if the conductor and the electric field of the external force they both are not equal to 0, electricity and electrostatic force they both are not equal to 0, then we can say it as it is an dielectric. If it is equal to 0, then we can say it as it is not a dielectric, or it is a conductor. Like that only polar and non-polar. So the second thing, polar and non-polar. So see here what happens here in H2 two atoms, they both are not joining. Polar means they both should be joined. See here a symbol is getting, or it is joined. Here see you can't join like this. So what means in non-polar you can't join that symbols. In polar you can join HCl like a straight, or like a downward, like a horizontal, vertical. However you should join, you can join. It should be symmetric and dipole moment it should have, and whether the centers may positive or negative charge or separately, it does not matter, but it should have joined. But if it is not joining, means it is not polar. The non-polar polar. If it is joining, then it is polar. So here also you can see the dielectric development in net polar or non-polar molecules or polar molecules. So here non-polar molecules, they both will be having positive and negative like circle, where electrostatic force is equal to 0. But if it has positive negative charge in a straight, there the electrostatic force, see here there will be gap between them. So if there is gap and it is like a oval, E is not equal to 0. So if here see, they both are in different shapes and they both are what's here, one is up, one is down, the electrostatic force is one is up, the electrostatic force one is down, and one is up, here positive is up one side it is down. If it is like that, then it is electrostatic force is equal to 0. But electrostatic force is not equal to 0 when here all the things here electro plus or upside only it is, So remember one thing, if electrostatic force, if it is equal to 0 in non-polar, then the positive charges should be up and negative should be down. If electrostatic is not equal in polar, then the positive charge will be beside the negative charge in the non-polar molecules. And if electrostatic is equal to 0, then the positive charge will be sometimes up, sometimes down. And if the electrostatic is not equal to 0, then the positive charge here, all the positive charge are beside or down towards the negative charges. If it is like that, then it is not electrostatic, it is not equal to, electrostatic is not equal to 0, we can say. And here thus in either case, whether the polar and non-polar, a dielectric develops a net dipole in the external fields, and that net dipole or polarization, and the dipole moment for per unit volume is called as polarization. So remember this, the dipole moment in per unit volume is called as polarization, and it should be denoted with P. It should be denoted. They may ask what is polarization means. And for P is equal to Xe by E is the formula you are taking. And here a uniform polarization dielectric amounts to index surface charges density but no volume charges density. So see here, electric are there, and here polar down, electric polar, and this is minus theta, this is plus theta. See here, all are like this. See here, all are beside. So here what you saw, if it is beside, electrostatic is not equal to 0, like that only. This is because the positive charge of a dipole sides closely towards the negative charge of the adjacent dipole. However, the surface of dielectric normal to the electric field, then the net charge density as an union neutralized at the right surface, and the negative ends at the left surface and are unbalanced charged. So there are unbalanced charges as it is closer to the negative, they both gets collaborate with each other, and it becomes unneutral in some parts, and in some parts it becomes neutral or equal, it becomes positive. So say see here, some surface has both positive and negative pi or sigma, we call it as sigma formation. But here in some places there is no pi, and in some places there is pi and positive and negative pi sigma formation. In some places, in different places, there should be both positive and negative sigma problems. Okay friends, like the video, comment on my video, and subscribe my channel. I'm in coaching center for more video. I will explain the next topic in my next video. So till then, take care and have a nice day friends. Bye.